Okay, so welcome to today's lecture in neural networks and deep learning. Before we start with our today's title, which will be on knowledge distillation, I should discuss the evaluation with you. So first of all, thanks a lot for everybody participating and giving feedback. Um, when I see the results, I'm quite happy that in average, at least you seems to be happy with the lecture, giving the overall grades and the feedback. So thanks a lot for that. Of course, you're not happy with everything, which is how life is. Uh, as I understand it from your, thanks also for the written feedback, the main concern is that you would like to have more text on the slides, or like slides which you can better use for learning afterwards. As I think I've said at the beginning, during my presentation, I like to have very few words on the slides because you should listen to me and not spend all the time reading. That's why will not directly change that. But of course, I hear that you want to have something like that. So there are three things in this direction happening a bit. First of all, I mean, what you can always see, and hope I know you know it. There is a full transcript also on the lecture translator website. So when you go through the last slides, you can also see what I said during the spoken. You might even see the summary. That might be helpful for some, but it seems I was hoping that's what you want to have, but it seems you want to have more. So yeah, this year I can't change anything. I will think what is possible to further improve it. Of course, also opportunity for you if you think this is a nice topic, how AI can be used to make enriched slides. That might be an interesting thesis topic. So if you're interested in that, also send me an email or come by and can see whether this is, I don't know where you are, bachelor or master thesis topic. I'm happy to discuss that with you. Yeah, so with this, let's have a look into how knowledge distillation works. So what we're planning to do today is we start a bit with motivation. Why are we talking about this? And that will be covered in all of this week. Today we'll do knowledge distillation, and on Wednesday we will do quantization. So where it's all about making models smaller. And then we'll explain what knowledge distillation is, and then look into three different ways of how we can do knowledge distillation. So called response-based knowledge distillation, feature-based knowledge distillation, and relation-based knowledge distillation. Then you know that there's some additional challenges when we are going into sequence models. So we'll review like what might be different in like sequence models and how they can be addressed. And then in knowledge distillation, there's a strong relation to data augmentation. So we'll also have a look at one example of data augmentation on the case of machine translation. But in general, this type of data augmentation is very common and will come again in when we look at additional applications where we'll mainly focus then on like how knowledge distillation, especially in large language models, can be done and is done to do that. But as I said, we will start with the motivation and look why you should consider this. If you look at what is happening currently, you'll see that the size of models is really exploding. This is only till 2023, but now we have even larger models. Of course, it's not that it's like maybe going as exponential at the moment. We're a bit saturating, but still, really like models that are currently state of the art have like 70 billion parameters or something like that. So we have really huge models, which might be okay for doing some type of testing. But if you really want to use these models in real world applications, it is a challenge because it's expensive, it uses a lot of energy. We want to be sustainable. That might not be the right way. So the question is, can we somehow get also good performance with somehow smaller models? And of course, the first idea you could have is you can just train a smaller model. And that is a good baseline. But what I hope I'll convince you today and on Wednesday is that on Thursday, that it might be better not to only train a small model, but we somehow can get some of the knowledge from the big models into small models and then achieve a better performance per model size. Of course, we might not be better than the really large models, but if you're only a bit smaller, but you only need half your energy or half your cost, that might be still good, because there's always this type of trade-off between number of runtime, or we see different, like model size can, of course, be defined in very different ways. We'll a bit look into that, but in general, this concept of model size and performance. And that especially is getting even more important if you want to apply these models on many devices. So currently, mainly everything works in the cloud. So there's huge GPU clusters somewhere in the world where you run your models, and then you can apply that for the big models, which is in a lot of situations good. We have internet a lot of times, but it might not always be the thing due to several reasons. You want to have it maybe also if you're not connected. It might be that due to privacy reasons, you don't want that everything gets sent over the internet. So if we are going to use strong models on mobile devices, on robots or so, then we have to see how we can get a decent performance without this like huge amounts of calculation that is needed. And that's what is our aim for today. So can we build strong models on small hardware? And we will try to have a look at what can we achieve then. If we think of these models, of course, there's two main tasks that we have to do. On the one hand is the training phase, and the other thing is the inference phase. Now the first question is, which one? I mean, of course, we maybe want to improve everything, but which is more important? Do you have an idea? Would you, if you're now targeted, would you improve the training of the model, or would you improve the inference speed? Which would you focus more on? Any ideas? Yes?
Well, in the industry, I'd say the inference is more important.
That is correctly, and so that is one part of the answer. So definitely, if you're building for the industry, you will train the model once, and which is very, very expensive. So I mean, I think for like big language models, for Llama, at some point they reported, and it's like you have to invest millions just on GPU hours to run that. But if you're successful, at least it will be used for a long time and by many, many users. So in total, most of the runtime is on testing or inference. So you'll have to optimize this type of inference speed. In research, it's maybe a bit different. So if you write your thesis, not sure, but most probable what you will do, you'll build many different models, you try them and compare them. So most of your time you'll spend on training, and then you will like have to look, and then you run it on a fixed data set, you test it, and then. So it might be on that case that you're more interested in training. Therefore, of course, it's somewhat important to optimize both. Today, we'll more look at the last case. So how can we get a very, like a small model which is efficient on the test case? But you should keep that in mind. That might not be the best solution for everything. And what we're talking today about knowledge distillation, even the training is somehow getting more expensive because we're training first a big model and then we're training another small model. So we have even extra work then, but with the hope that it will like over the long term, because now you can do inference on a very small model, you'll get somehow better on that. And then, of course, there is very different dimensions what you have to think about how you measure how much is needed. So the one thing is that you want to maybe the resources you can use. It can be on the one hand runtime, you want to have a fast model. It can be also memory. That means you want to have a model which fits on your GPU with only like 46 gigabytes of memory. And of course, there is a correlation. Often you can, for example, reduce your memory size, but increase your runtime. Any idea how to do that? Very simple trick. You reduce your batch size. So if you persist every example only once, you only have to store one example, and the weights, if you do like 1,000 examples together, you're a lot faster because that can be parallelized, but you have to store everything. So there is always a lot of constraints. Also, like whether you use your model on a CPU or a GPU and so on. To see that what you're trying then typically to get here is something for machine translation, but in general in neural networks. So here is a bit like how many thousands words you can translate per wall second. There is your quality measured in Comet here. And what you want to go is up to there on the top right. So you want to have like very good performance as high as possible, but many words outputted or processed per second. So, and then everything, for example, and this was an evaluation, everything where now nobody is better and faster would be a winning system. So here you have 5 winning systems. This one, and this one. And that would be then a bit your trade-off, what you have to take. Do you want to more focus on quality or more focus on runtime? But what you can see is that these models are definitely better than this one, because this model, for example, here has a lower runtime and a better quality, so you would prefer this one over that model. Then I said you can easily improve your somehow throughput by doing batching. So you process a whole document and processes in parallel, but you have to, of course, there also think about restrictions. So can you do this type of parallelization? It depends on the application scenario. So you can sometimes process a lot of data, which is there, but in inference, if the users will do requests randomly and maybe not too often, then you have to do requests one by one, and you can't do this type of parallelization, which again, like, let's think about, okay, what is the right way to make these things efficient and so on. One thing which we'll not talk about today is that, of course, also the implementation is important. So there's often like different implementations, even of the same network. Nowadays, you can normally, for example, use like the PyTorch, which you use for training, which uses Python, and then there's dedicated optimized inference servers, which can improve your throughput. So there's also this idea, even the same model can be served slow or fast, depending on like how you optimized. If you remember, quite some time ago, we talked about CUDA kernels, so you can try to optimize and have dedicated CUDA kernel. So there is a lot of implementation work also where you can also optimize your runtime and your memory footprint. Again, that will not be the main focus, but you should think about, yeah, if you want to build a model which is really efficient and which can serve a lot of models, these are all considerations that you should take into account to build then a good model that can be used. When doing this, as I said, there are several trade-offs that we have to take. The one trade-off is like about throughput and memory, where it's like typically one easy way to control that is the batch size. So the larger your batch size is, the more throughput you get, but also the more memory you have. You can also think about that, if you're having the model split about 2, you can have maybe a larger model, but then it has to be calculated at 2 GPUs. So there is a trade-off between how much memory you use and how much throughput you get. Typically, what we have also is that you have the trade-off between quality and throughput. So I hope that become clearer during the semester. A very easy way to improve quality of most networks is to just increase their size. Of course, until some threshold, there's data restriction you've heard about, but in general, you can get a higher quality when you let the model get bigger, and this comes then as a cost. And that's what we want to look at today is, if the best model is a very, very huge model, can we somehow get this knowledge also into a smaller model? And the idea we want to do there today is what is called the knowledge distillation. So the idea is, can we somehow get the strong model on small hardware? And the idea is we build once a very, very large model, which has a very good quality. And then we're trying to extract this knowledge and put it into a small model. And then we'll see that hopefully this is better. So that's the big question that we have to address is, why should a model which starts with a big model and then distills this knowledge into the small model be better than you just train a small model on the small data? I hope with the ideas we are discussing today, I can convince you that this is a good choice and this is possible. And we'll find some hints why this is helping, because it's a common technique that is used. But that's, of course, an important question you should ask yourself. Why is it helpful to first train a big model, then use that to train a small model, and then throw the small model, the big model away? Which, in the first view, I hope you would all agree, doesn't sound too convincing. So we'll have a look into what could be the right way to do that. Okay, so this is the basic idea of knowledge distillation. Before we're now going on, do you have any specific question? Okay, so the definition of knowledge distillation is one idea of what is called model compression. So that's what I said is what we're covering here, that we're looking how can we make a big model smaller. And the methods we're doing is that we're training a small model to mimic what a pre-trained very large model has been done. The idea is already a bit older, like the first idea was proposed in 2006, and then most famous mentioned is the paper in 2015 by Hinton, where they tried to generalize that on the idea of knowledge distillation. How does the general setup look like? So the general setup, we're talking now typically about two models. We have the very big model, and this big model, because it has a larger knowledge and we want to transfer this knowledge to the other one, is typically called the teacher network. So we have our teacher network, which is the last one, which gets input. We put it through the teacher network, and then we're getting some outputs from that. What we're interested in, what we want to improve, is our student network, where we take our input, put it now through a smaller network, and also get output probabilities. And now the first question is, how can this small network learn? How should this small network learn? Because what we want to do is we're taking the knowledge from the teacher network and distill it to the student network. Any idea how you would now train the student network based on this motivation? Yes?
The output of the teacher network as like supervised learning labels for student network?
Yes, exactly. So that is then what people call a bit the distillation loss. So you take your output probabilities and you're trying now to make the lower one, the output probability of the student network, as similar as the ones from the album. What we now can do is we even have significantly more information. So normally we only know what is the right answer. That's what you get in label data. You get this is the correct label. What you can do in the training setting of the knowledge distillation is that can even compare somehow the probabilities. So we can try to make these probabilities the same, which you can think of already, that you have a more more richful information, because you're not only saying, but this is a good one, you're also saying this is decent good and this is really bad, and so on. How you can, for example, do that, and we'll come to that a bit later, is that you measure like the difference between the two distributions. So you have the output distribution from the teacher network and from the student network. Now let's assume we start very easy. We just have a classification task. In that case, what the output normally does is a distribution about all possible classes. So imagine you have an image network which classifies the cats, dogs, and rabbits. Then you have three probabilities in the end, and you have these three probabilities. What you now want to do is like this, these probabilities are a bit the same, and you can measure the distance, for example, using the Kubrick library divergence, which is the sum over all possible events. So here it would be cats, dogs, and rabbits. Then the probability of the one time log the probability of the one divided by the probability of the other one. And what only has to be keep in mind when you work, so this Kubrick library divergence, we'll see it's often used to compare to probability distributions. What you have to keep in mind is that this is not what is mathematically a distance. So it can be used to compare them, but it's not a distance, meaning that the distance between two, the direction is important. So the Kubrick library divergence between P and Q is different than the one between Q and P. Which for distances, if you go from A to B, it doesn't matter if you go from A to B or B to A, the distance in a metric should be the same. What you also, of course, have is you might also have the output. And then you can have additional signal here. So what you can, of course, also tell the model is what original should be done, so that you also have some type of classification loss as additional knowledge. And we'll see what else on losses you can do. But what you should keep, of course, in mind is you typically still have your training data with input and output. So you can also train your teacher-student network. Now you have additional information. You once have what the humans told you and what the teacher network tells you. Why is this so what is now the big advantage of this type of approach where you have different things? The problem is if you're doing the normal cross entropy loss. So for example, you're doing machine translation or some text generation task. If you do cross entropy loss, then we improve the probability of the correct solution, and all the others we try to decrease. So the training signal is normally in cross entropy loss is that this is the right solution and all other solutions are bad. Of course, that's not true. Often we have ambiguous tasks. If you think about sentence generation, it can be that some are good and some are better, but there's not like the one is right and all the others are wrong. So the problem is that this training data is typically not this fine granular. So you have only the one single correct solution, while in others there are many good solutions. Another example is information retrieval. Think about things like Google. I mean, there is like several good answers or like documents which might help you. There's typically not the one correct one. Of course, it's not always the case. If you think about speech recognition, typically I have said one sentence. So this is the correct sentence. All the others should be somehow wrong. But a lot of tasks, if you think about chatbots, there's not the one right way to answer. There's several right ways to answer. And this is not reflected in your training data. Your training data tells you this is the right answer, and you train it to be that all the other answers are wrong. There's a bit of way of how this is modeled and why it's still, I mean, it can't be that bad because it's still working. You know how that is a bit addressed in training large systems. And typically, if you have real data, sometimes the one answer is given and sometimes the other answer. So you have like all the correct answers hopefully occur at some point, and only these occur. And if you then average, so all of that gets a bonus, a better, and all the others only get negative. So you're in average, get a bit of this type of feedback, but only about like if you average over many, many examples. So because you at each single point, you only get this is right and this is wrong. In contrast, for the student-teacher learning, you're not only getting, if you look at really at probability distribution, you're not only getting this is right and this is wrong, but you're getting this is at a high probability, this is a bit lower, so it's a bit worse, and this is really completely wrong. Of course, only assuming that your very, very large model is a good teacher. Because, I mean, if you do student-teacher learning, the learning is only helpful and good if your teacher model is good. You can only learn what the teacher tells you, and other things you might not be so good. What you, of course, should then also keep in mind in the scenario is you should also have this a bit of a baseline. So you're only, I mean, training your small model on the normal data is your baseline, and student and knowledge distillation is only interesting if you really get better than this one. If your final model is not better than this one, it's a bit of the question how helpful that is. There's a bit of variation of that. If you think that you might be for some task only have input data and no output data, so you can't train it supervised, then things might get interesting again. But generally, you assume that your teacher has been trained on this data because it has to have learned it on some way of that. And so you should have like supervised data. And then, of course, this is a baseline you normally should compare to. When we do this student-teacher training now, there is different ways on how we can train the model and how we can like try to convert the knowledge from the teacher model to the student model. The first one is one we mainly have discussed until now already and a bit motivated, is what is called response-based knowledge distillation, where the idea is the response of the student should be the same as the one of the output. And there is two ways. There's the standard where we really look at the probability distribution, so the probability should be as similar as possible. There's also the weaker one where you only say the most probable one should be same. Then it's more going into data augmentation, and we don't have the benefit anymore that we saw because we only look at the correct one. In the standard case, what we want to have is we compare the output probabilities of the teacher network to the output probabilities of the student network and want to have them as similar as possible. But of course, this is a bit weaker. I mean, it's a stronger signal than just looking at the outputs. So we get the output probabilities, but we're not looking at the teacher and the student. So it's a bit of a black box method. You don't care how your teacher really looks like, your network, and how your student network, which has a big of advantage. You can use any model and like distill any model to any other model, coming, of course, to the cost that, yeah, you also don't benefit from internal representation that you might have learned in the teacher. And if you remember of like what we discussed in hidden layers and so on, so it might be very interesting semantics that you learn within the teacher model. So it might be helpful to also take this into account. And that is what is done in so-called feature-based knowledge distillation, where the idea is now that we're not only looking at the output probabilities and trying to make them the same, but also some hidden representation in between. So you try to give a stronger signal. So the teacher is not only correcting you if you're doing the right answer or the wrong answer, But the teacher network also looks how you get there, which in neural networks means like which hidden representation you calculate in between, and it forces the student to do some or similar calculations. I mean, this is no longer a black box, but you have to look into the internals. You have to define some type of mapping, so it's not as easy anymore. But the hope is if you give a stronger signal, again, the idea is you give a stronger signal so that then the model can more strongly do the same things. Finally, there's what is called the relation-based knowledge distillation, where you look what is happening. You're not looking at the absolute value, but you're looking in the student network, which calculations are done. What is some relation between some layer and some future layer? So which calculation is happening between the delta between some calculation? And you try to do the same thing then on the student networks. Yes?
There's a mistake in the slides that are on the Ilias, because in our slides there's still feature-based knowledge on the slide in the graphics.
On
Like
this
graphics where on your slide there's relation-based, and like at least on the slide that I downloaded at the beginning of the lecture, it says feature-based.
Sorry, I mean, I have to admit I didn't check them today. So thanks for pointing out. I'll update that. I'll check that later. Thanks for pointing out. So yeah, so hopefully now not the remaining of the slides are wrong, but the idea is that here you're not looking at the absolute values, but you're looking at the values in between, and you're checking how like the hidden representation changed. And the change in the teacher network should be the same as the change in the student network. Okay, so these are the basic three ideas. And for the next time, this will be then what we'll look into: response-based knowledge distillation, feature-based knowledge distillation, and relation-based knowledge distillation. But before we are going there into details, do you have any question? Good. So as I said, so the response-based teacher distillation, the idea is we have the output of the teacher's response, and we're trying to measure the difference now between the one of the teacher and the one of the student. So you have now two things. How would you measure the difference? How would you compare them? What type of loss function would you use? Any idea? You have the probabilities of the teacher, you have the probabilities of the students. How do you now measure the difference in order to then use gradient descent to improve the student network? What you mainly have is two vectors, and you somehow need to compare them. So what can you do there? Any ideas? I mean, the first thing we can maybe do is let's look how we're normally doing. We also have two vectors. We have the reference vector, and we have our probability distribution if you train normally. And what we have learned is that we typically do that with our with a cross entropy. If you look back, the cross entropy was defined as the sum over all possibilities, the reference value for that times logs times the output probability. This was a lot simplified in often the cases, because typically we have a one-hot representation, so only one value in the sum is not zero, because only there where, and then you just have the logarithm of the output probability of the correct solution. Because for all not correct solutions, this is zero, and then it sums up. But since now our reference will be not like a hard threshold, but a probability distribution, we're staying with the original formulation. So what we can do is we can just replace that now by the teacher. So the teacher has an output for each class, and we take times the logarithmic of what the student says. The outputs of teacher and students are both probabilities, so the probability of the teacher network for the input and the probability of the student network. So let's say the teacher network has a probability distribution P, and the student has a probability distribution Q. Then the difference between P and Q is just the sum over all our classes, the probability of P times logarithmic the probability of Q of that. So that is like the loss function you're trying to optimize. And trying to use the same type of normal loss we're doing that we're trying to optimize. And so we don't have to change a lot. The only thing we have to change is that instead of the labels in normal training, we are now using the teacher's output. More interesting, it's even strongly related to what we're doing in that we're directly even optimizing the Kubrick library divergence. So what we said, the possibility to compare both. If you remember, we just introduced the Kubrick library divergence between these two as a sum over all possible classes, P of x log P of x divided by Q of x. Now you can use some basic math that the logarithm of a quotient is like logarithmic of the first one minus logarithmic of the second one. So that's just the basic logarithmic rule. Then you can take the P of x separately. And if you then look at this one, what is mainly is our loss we had just before. That's here our loss. So this one we're optimizing, and this is something depending only on the teacher's network. Since the teacher's network, we're not changing, we're keeping that fixed. And that is important to keep in mind. If you're training now, of course, the teacher network is what we have. We are only optimizing our student network. So by optimizing the cross entropy, we are also optimizing then our Kubrick library divergence. So we're trying to make these two probability distributions as similar as possible. Any questions to this? Of course, there's other ways. So now we looked at one possibility loss to compare them, which is the cross entropy. Now, if you saw that, do you have another idea how you could also do it? Had this loss already quite a lot of times for other use cases. And the other thing is you can just reduce the L2 loss. So you can just try to make these things two more similar. So what is just the sum over all differences, squared differences between them? So you take the probability for one class from the teacher network and the probability from the student network. You look at the difference, square root, and then try to minimize that. Again, trying to make these two the same. So in this case, you're not interpreting this more as a probability distribution, but just as two vectors. They have the same size because the student and the student network and the teacher network are like defining a probability distribution about the same event space. So you have exactly the same classes, and then you can try to do that and predict the same thing. So this is just a different way of how you can do that. So to summarize what we have in response-based knowledge distillation. So first, we're only making use of the final output, which has a big advantage that it's independent of the architecture. So we can also do knowledge distillation, for example, from a transformer-based model. And then if you want to do if you remember state space models, which might be faster inference, they don't have quadratic runtime with the length, you can try to convert this knowledge into a state space model. So you don't care really what is happening inside there. You only look at the output probabilities. Of course, the only restriction is that your output is exactly. So you have to do the same type of classes and classification. Or if you think about more language models, it has to be somehow the same vocabulary. So it might get more difficult if you have their different things. But this is the only thing you can do. Also, you have a stronger supervision signal than just training data. We are not having hard information saying this is the correct solution, everything is wrong. But at each time step, for each output, you get a probability distribution saying how good each one is. And that is a lot stronger signal. And I hope this can already convince you that this might be more powerful than training the model just from scratch. Because you're not only telling you this is the right one, but you're also telling it like how good or bad are the others. So you get a lot more feedback signal. There is an additional advantage. You also get very consistent feedback. For the same input, a network will always present you with the same output. And that's maybe easier to learn than noisy real data where some is wrong and sometimes you get the one input and sometimes you get the other. So here you always have some of the same type of signal, which again makes things easier. But still, we only have the supervision signal at the end. And we already said at the beginning, it might be better that we're not only getting the signal at the end, but also getting in between signal. And that we want to look at the so-called feature-based knowledge distillation now as our next step. So how can we do that? So the idea is, yes, we typically will look at the final output, but we want to also now take these two as white boxes and also try to use feedback signals here and not only make that the final layers are the same, but also in between. So of course, no longer as straightforward because the final has to be the same. If you do a classification with 5 classes and your small model should do the same class, the output layer should be the same. But typically the internal structure is now, of course, different. So the very easy thing to go from a large model to a small model is to reduce the number of layers, to make each layer smaller. So, but if you do these things, of course, it's no longer as easy to make a direct comparison between these two. So the first question is, what do we want to compare? And one way of comparing is to compare the hidden activation. I think that's quite maybe hopefully also your first way. Then if you want to compare what is happening in the network, you're comparing the hidden representation. However, there you have now exactly this challenge that if we want to compare the hidden representations, that the network can be different. And it can be different in several ways. What would be your ideas? What can all be different in this type of network? So if you parameterize your network, what are the things you have to decide on when you set the architecture of the network? Any suggestion? Yes?
Number and the size of the layers.
Exactly, that's 2. There's one more. Maybe I gave that already away and you're not thinking about it anymore. I mean, the last one is also the type of the layer. So do you do self-attention or state space? But exactly, so these are the main things. So if you have specified the type, if you have specified the number of layers and the layer size, or if you have different types of mixing, you of course have to make a more detailed description. But if you describe that, it's a clear description of your network. So let's see what happens and where we can do this comparison. So the first question is the layer type. And there we have to say, for now at least, we are ignoring that. If you want to distill like a attention-based network into a state space model, maybe that's possible with feature, but it's getting complicated. So for now, we're not considering. We're assuming, we're restricting ourselves that the student network has the same type of layers than the teacher network. If you want to do something else, you can do, for example, go into look for output-based, so response-based knowledge distillation. That all works. But if you really want to compare the features, the hidden representation might not be the best thing. The next is then the number of layers. And what is there typically happening is that you have to by hand define some type of mapping. So where do you want to do the knowledge distillation? Typically that's that's very straightforward. You do some type of linear things, for example. So if you're saying, oh, my small model has half the number of layers, you maybe do that the first and the second should be the same, the second and the fourth, and the third and the sixth, and so on. Or you maybe also skip some, so that is now a bit the hyperparameter, which layers you compare. But that's what you strongly enforce, and you're like, by defining your knowledge distillation loss, you're defining which layers you compare between the small model and the large model. Then the last thing is the different layer size. And here things are, of course, a bit more complicated. So for the number of layers, you can by hand define which ones to map. If you now have like one layer which has 1000 dimension and the other one has 500, might be a bit difficult to by hand define, yeah, layer 1 and 2 should be somehow, no, hidden size 1 and 2 should be the same as 3 or something like that. So what has been there suggested is that instead we are learning a mapping function also, and then we're trying to minimize the difference with an optimal learning function. So you should first learn somehow a mapping between the hidden states, and then you say with this, with the best possible mapping between the two hidden sizes, how similar is it? So what you can do is you take your hidden size of the student here, HC, you map it into a larger size of the teacher, and there you take now, of course, a simple network. You don't want to have there a lot of calculation. It just be that, yeah, you're just ensuring that somehow things are a bit more compressed, and then you're comparing it to the hidden size of the teacher network, and these two should be as similar as possible. So thereby, you're mainly minimizing how similar are the two hidden representations if I found a very good mapping between the student and the teacher network. Meaning, yeah, if this mapping exists, you're not putting any information in there, then all the information which are in here should be in there. So you'll not make it perfect, but you're trying to minimize a bit the information that are in the other network and still be a very good type of quality. What this now means is, so if we're doing the hidden activation, is that we have a quite strict supervision. You mainly say, oh, these networks, these layers should learn exactly the same thing. These activations should be exactly the same, which might be good. It's maybe easier to learn it. On the other hand, you might have also the disadvantage that, yeah, you're restricting your small network too much, and maybe it has to learn a bit different to have the same power than the larger network. So that might be also challenging to have the right supervision. But it's one good way to do it. There's another way how you can try to compare the hidden activations between the two networks, and that is we're not directly comparing the networks, but we're mainly thinking about which input are they using. So what you can do there is you somehow measure which input of the current network is important, and you're trying to force that the same network takes the same input into consideration. Again, think about an image classification. If you classify a dog or a cat, it might be good to look at the dog and look at the face. So both networks should somehow focus on the same thing. That is maybe a good signal. So, or like the teacher can tell you, oh, if you want to understand this sentence, you should mainly look at these 3 words. And then you're trying to enforce this also by the student. And this can be done, for example, by image classification, but also by NLP. We'll look, and what you're mainly doing is some type of attention map. We're doing not only attention of self-attention, but also of CNNs. And we are looking, okay, which information is most important. And then we are trying to make sure that these two are the same. So to make things a bit more clear, let's start with the vision-based model. So this one is one way of doing this for a vision-based model which uses CNN networks. So if you remember CNN networks, they are put over that. What you can then do is you have for each pixel, so wide times high, you have different channels which learn different types of features that got activated for each of the pixels. What you now want to do is, of course, you want to map it back to the original image, mainly saying, okay, how important is each pixel in your CNN? How much activation does it put into my network? So what you're doing, if your hidden activation here is that you have something like wide times height times the different channels you have, so the different activations for each pixel, you want to have a function that removes the channels. The easiest way of doing that is, of course, to just say the sum of all. So when you have now some hidden activation for each pixel, you're just summing the absolute values of the activation and thereby interpreting them as the more activation there is for one pixel, the more the image will focus on it. The thing about that you do later maybe some max pooling. That's a bit what is happening because you always then look at the max. So there where most of the activation is, there will be also most of the attention put to these pixels. So that is the first thing. We're defining for the different layers to which pixels they are more focusing, which does the most activation in your neural network by summing over all your hidden dimension here. And this will give you then this type of map, which is based on your input size. So it's now independent of your hidden size here. You have summed over your hidden size. It only depends on your input size. And you're putting, of course, the two same images in there. And what you can now do is like at different steps. So if your teacher here has 3 times 3 hidden layers, the student has 2 times 3, then always between there, you compare your attention map vectors. So that is like these attention maps, which is these metrics. You do the difference at each position. And the dollar one makes it relatively. So saying mainly that, yeah, if 50% is here on this pixel or 10% is then pixel, then it should also be 10% as a pixel of the other network. Assuming that at this position, at this position, and this position, the network should like focus on the same part of the network. Again, the motivation is if this is a dog, it should focus on the dog and not on the grass, which is around there or so. Any questions to this type of idea? One thing where it might be even more intuitive is when we're talking about attention. So I go to attention-based models, and there is an example here from large language models, language processing. So you remember we have the self-attention, and there it seems to be also attention. So in the self-attention process, we're always attending to the different sentences, and this is the alignment matrix that you have. Understanding for each word to which other words does it attend. And you see, of course, the model is a bit most attending to itself. It's mostly trying to understand itself, but it's also looking at other things. So, for example, here there is a bit more attention. Here is more want father, want nothing to do there. Yeah, so here is this one is attending. Here, these two are important, and so on. So how do we get that? This is just the normal attention. So what we're really like visualizing is here, to remember how we do the attention, we have the query of the current word, and we are comparing it to all the keys. And that gives us the attention values, which we then normalize to sum up to 1. And this is what we have visualized here. You see, it seems to be a decoder-only model because you always only attend to your previous words, but you can't attend to the future. So it's a mass self-attention, but then it shows you nicely to which words the model is attending. And now we can do the same thing. If we have this pattern, This pattern now not depends on your network architecture, how many heads you have or anything. This only depends on your input. It's like an input matrix, input size times input size. And then we can again say, if the teacher model tells you that in order to understand this word, you should look like at these words, and in order to understand this word, this seems to be also important, then you want to tell that to the student model that it should do the same thing. So here we can do the same thing, and that was done in like TinyBird. So you're not only making the hidden states as similar as possible, you also have the attention loss, where you generate your attention matrices, and then you try to calculate a loss between them. Again, the attention matrix, because they only depend on the input size, they are the same. And you can, for example, just do a mean square error between the two matrices and try to minimize the difference between these two. Good. Any more questions to this type of model? Yes. Oh, sorry.
What do you do with your multiple heads? Do you average them?
Yeah, typically what you would do then is average them in order to get a bit the same. You can, of course, also try others. If you think some heads are more important than others, you can also have individual losses. But I would say the normal thing is that you have like an average of all heads and do the average of the other heads. Good. So the last thing we want to have a very brief look is what is called relation-based knowledge. So in that case, if we want to transfer the relationship between different layers from the teacher model to them. So what we are doing is we are looking at two layers of the teacher model. We are looking at two layers of the student models. We are comparing the features of these two layers of the teacher model and the two layers of the student model. And then we are saying the difference between these two, they should be the same. And the interaction between these layers should be the same. How is that done? So we're in this work, they define their interaction between the layer I and J as you look at the activation of the one layer and the activation of the other layer, and some overall position. So in this time, it's only based on your hidden states in both. You're averaging over all positions. And what you then make is you look at the correlation between the hidden states. So mainly what you look into, in average, the first hidden state of layer I, how is it related to the first hidden or like the channel of J? And that will be the one value in your final matrix you get by multiplying these two hidden states. So this one is mainly describing how dimension 1 and 1 interact. This is how dimension m and 1 interacts, and this describes how dimension n and m interact. So you have this cross product of all dimensions m and n of these two feature maps here and how they interact. So for example, if dimension 1 is high, then also dimension 1 in the other layer is high. Because this is randomly ordered, so it can be very different. But the general idea is that you try to inspect that. How is the relation between the features here and the features here? And then you store in this matrix G, which compares them. So it compares how the different challenges in these two layers are happening. If you have that, now, so you have this relation between what is happening in the hidden states in the one and in the other layer. And if you have now two networks, you can compare this interaction between these two hidden states, for example, here in network 1 and in the student network, you have two matrices and just do the difference again. So you do that over all these possibilities here and always compare how these matrices are. Again, saying that, oh, the calculations that you do in these 5 models, in the big models, should be somehow the same as the calculation, or should approximate the calculations that you do in these two layers here. So again, it's telling the model now not that the absolute values are the same, but it should tell the transformation that you do in the 5 models up there should be the same as the transformation that you do in the 2 down there. Of course, this only works decently if your channels, so your hidden representations, are the same in the two models, because otherwise your matrices here will have different sizes and they will not work straightforward then. Good. Any questions about this knowledge distillation? Good. Then for the next, we want to look a bit at one more specific thing on sequence modeling. So first, before we're looking into why it might be more challenging, what type of sequence models do you remember? How can you do sequence generation with neural networks? Do you remember any architectures that we discussed there? Any idea? You had mainly two different architectures. I know it's a bit of a while ago. Anybody remember? Let's start with, we have definitely, do you remember we had encoder decoder models? So there the idea was we take our input, we encode it somewhere, can be text, can also be image, and then your generation of the sequence is by a decoder, which will generate here the answer, where it's Karlsruhe in Karlsruhe in German. So you have this autoregressive type of decoder, and you have to connect them. So that's like an encoder decoder model. Now it should be straightforward. There was a very similar approach, a different network. Does anybody remember? We had encoder decoder model, and we had one other model. Any? The other thing is even simpler. It's like we're doing the decoder only model, which will just like connect those. We're not having separate encoder and decoders, but we'll have this type what is now also used in large language models, decoder only, where we are having only a decoder which first reads in your input and then generates like word by word your type. So these are two models which can be used to do generation, and they are doing that in this like autoregressive way, where you start with your empty sentence in the decoder or with your prefix, and then you generate a probability distribution over all possible vocabularies. Then it depends on your sampling strategy. The most easy one is greedy decoding. You just take the most probable out, you put it in here, you generate then the next token, put it in there again, and so on. And this way you generate until the end. Does anybody remember when we stop? What is the typical stopping signal for this autoregressive generation? Yes?
Yeah, when we predict the end token.
Exactly. So we predict at some point the end token, and then we're stopped. If we now have this type of thing where we have our student network and it gets teaching signal from the teacher and maybe also from the reference, we do a classification. I mean, we do the one loss from the output and the one loss from the teacher. Do you see anything which might be challenging, or why it might not be super straightforward? We said maybe it's nice to have both losses. So once you do the classification loss, so on your real data, and your distillation loss, which compares it to the student output, do you see anything which is in this type of sequence models might be a bit challenging? Yes?
Yeah, maybe if we use autoregressive predictions during training and we have different sequence length.
Exactly. So that, sorry.
Then we could use teacher forcing.
Yes, exactly. So we have a bit of the problem, and teacher forcing will be one idea we'll discuss several. But the challenge is now, I mean, if you have a classification, you have 5 classes here, and the probability in one of them is here. So you have exactly the same. But if you're now doing sequence generation, you have different lengths of your output sequence. It can be that this generates an answer which is 5 words, but the answer by the human is 2 words. So then it's hard to compare it, and it's no longer easy to do that. So the main challenge is how can we deal with this in this type of sequence generation, that we have different types of output. And therefore, people have investigated different ways of how to do that. There is, different ways of what you can do. The one thing is you can do like what is called word level knowledge distillation, where you now take the student output, the ground truth, and you force the teacher network to have the same probability, and then you just take these types of different probabilities. But where you're not encode is that maybe what you do this word level, where you just force a teacher to have the same output. So you can always, as we saw before, you can force the model to generate the right answer and then just get the output probabilities. What you're not doing in this case, when you're now, instead of taking the ground truth, I mean, what you really see here, as we had before, you're just taking now, instead of the probabilities, the one hot encodings, you're taking now here the probabilities, you have the same sequence length, so this works very nice. But what you're not doing is that maybe the teacher network was most probable generate some other sequence. So it's not really that helpful signal. What you tell the model here is like, all these probabilities might be relatively low, hopefully not often, but sometimes. So you're not really trying to distill that the teacher might go into a different direction, and that you maybe should generate the same type of output than the teacher. And therefore, word level knowledge distillation is a first helpful tool, but it only uses the probability distribution of the individual words. So that's word level knowledge distillation, but not the knowledge that the teacher has about the whole sequence, and that it might be good in guiding you to some sequence. And therefore, there's additional ways of doing it. So one thing is what is called sequence level knowledge distillation, that you're only using mainly, you're ignoring now the ground truths. So you're just generating output by the teacher network. And then you're using the best possible thing here, so ACF, and using that as teacher. It has the advantage that you're now learning really to generate how the teacher generates. It, of course, has also a bit of a disadvantage, because now you really need to do generation during training. The nice thing here was, for your teacher network, the sequence it has to do, so you can do that in parallel. So you don't have to do real generation. You can put the full input here at the beginning already, because you put in the reference and you only get the sequence. If you're doing sequence-based generation, you have to generate really the translation or the output by the teacher. And then you can use it as training data. What you now have is, of course, you're not only having the ground truth, but also you have the probabilities, and also can use that. That now depends if you only take the ground truth or everything, but you really look at the sequences. Has, for example, some additional advantages like consistency. In this case, now for the same input, the teacher network will always generate you the same output. So you don't have to learn this ambiguity by yourself, but you're directly telling the model, for this input, always generate the same output. This is mainly decided by the teacher network also, what is the best translation for this input, and the model does no longer decide. Of course, it also has no longer this variability in there. It comes, of course, also with a disadvantage that we're ignoring completely our labels from the training data. We're only trusting the teacher. We are not using any information anymore from the training data, but we're just learning what the teacher tells us. And therefore, there's also the third way of doing it, which is called sequence level interpolation, where we try to also integrate the knowledge from the labels. What you do is you generate now again outputs by the teacher network, but then you're not taking the best one as before, but now you're comparing these 3 possibilities or so by the network to your ground truth, and then you somehow take the one which is the nearest to that one. So of course you have to have some type of distance metric again, but you're trying to take a bit an interpolated way that you on the one hand trust what the teacher tells you, but not purely. If your data tells you something completely different, then you will also go from what the teacher tells you and also use that one here to improve. Good. Any more questions on that? Now what we have here already seen is a bit sequence level knowledge distillation. That's mainly a different way of data augmentation. And that's what we want to look at, so that, or now it's also sometimes called synthetic data. So one way of knowledge distillation is also that we're really doing complete black box. We're not caring any more about the model. And what we just want to do from the model is we're generating new training data, and then we're using this data to train our model. Of course, it comes at the cost that we are not having this strong signal anymore. We're not having the signal like what is good or bad, but we have some advantages. For example, we have the advantage that we get consistent data, maybe more appropriate data. And we want to look at one example where this was maybe one very successful use is what is called the idea of back translation in machine translation, where the idea is, okay, if we have a strong model or another model, how to teach is you generate translation, you encode in your data now the knowledge and try to use that. The nice thing is we don't have to adapt anything about our training data then. The only thing you really have to do is like generate the data, and then you can use all your other training examples again. So how that works is if you have now, you want to train on unlabeled data, what you can do is you can take your model and translate the unlabeled data into the target language. So you generate labels by your model, and then you have now generated new training data, so synthetic data. That's the first step. And then you can do your fine-tuning on this new data, maybe in addition to your previous one, and train a new model on that. So the knowledge from this model is somehow encoded in this data, and that is then used to train. What in this scenario is a difficulty is, of course, and that you always have to think of is like if you generate synthetic data, your labels aren't perfect. We've seen that just before, like that we, for example, tried to include then the annotated data from the beginning again and not select the most probable one, but from the probable one, select the one which is most matching to the data. Here in data augmentation, you typically don't have that. So you only have input data and you want to generate output data. And then, I mean, one thing, yeah, you can, I mean, maybe it's still better to have noisy output data than non-data. The other idea, which is also often done, is for a lot of problems, not classification, but generation problems, you also have the opposite problem. So for speech recognition, the opposite would be maybe TTS. For machine translation, the opposite is that you do translation in the other way. You have question answering and maybe question generation. And so what you can also do to generate your synthetic data in the inverse direction. So what you're now doing is that for your initial model, you're translating not from German to English as you want, but from English to German. When you now use that data for knowledge distillation, your input data is not perfect. But normally that's not as harmful because in reality, you will get good input data. What is important is that your output data is important. So here you see that now you switch the directions in the lower layer, and then you can use that one where all your labels labeled, your output data is human quality, and then you can try to train it this way and get the best results. And of course, you can now extend that and you can iterate it, and maybe like if you especially have several models, you can like generate more and more training data. You see, so there is synthetic data is not, or data augmentation is not only used to encode information from the smaller to the larger models. Now we're seeing this idea to transfer knowledge from one model to another can also be applied to models in different directions, to just different versions of the models and so on. So there's much more. And I mean, you can, of course, do that on your hidden representations, but there's also ways of purely doing that based on your data that you have. Good. Do you have any more questions about that? Then, like some more examples of, more things where distillation happens, and then especially where we also want to talk a bit how this is done nowadays in large language models. So first one idea is like, I mean, now we saw already with data augmentation, it might not be only helpful for like transferring knowledge from large models to small, but you can now apply the same model ideas also to other things. One idea is to apply it to yourself, what is called self-distillation or born-again networks. So what you train your model is on in the first step, and then you train your model in the second step, start again the whole training procedure, but they use information from the first to transfer it. And then you train again and so on, and you always transfer one to the other, and maybe you can even also. The idea is you get always more and more feedback signal. If you do a random initialization, you might learn always a bit of different things, and you're trying to add all these informations into the next step in there. So that you're not only having what the next model is good at, but that you also have additional information on what was in generally interesting. A similar thing is that you're doing it in parallel. That's the so-called deep mutual learning, where the main thing is you're now training not one network, but you're just training two networks in parallel. And then you're using the difference between the networks. For example, here again, the probability outputs, and trying thereby to keep the models the same. Again, the idea is to have a more powerful model. These networks are trained initialized independent from each other. So you have two versions of the classifier. And again, you're trying that you even get stronger by not training them independently, but telling the other model always from each other what it has learned. And then finally, where knowledge distillation also is very common, especially also in this data augmentation view on that, is in generally for large language models. Next week, we'll have a dedicated session a bit more about large language models, but just, I mean, you know how a language model works, you know that they're trained on large. So there is a lot of ways of how you can there also like address the ideas we had today in order to do knowledge distillation. There are typically three different scenarios in there. So the one is, again, you have like still most of the time you have some type of closed source LLM, and you want to take these knowledge into open source LLMs. And there we'll see there's one challenge compared to other tasks we see today is that is more in step one is definitely more the case of this data augmentation, because if you have a closed source solution, you typically don't get output probabilities. So that means you can only get the output, but this is still helpful, and we've seen it can generate more data and so on. So one application is to go from a model that you don't have and use that. And I guess you've seen there's a lot of papers nowadays which just generate data with language models and use them then to train. That is mainly that you're doing some type of knowledge distillation from your big model to the smaller model. Then, of course, you can also try to do self-improvement. So you can generate more data with the same model, use it again for training, and thereby improve the models themselves. Or you want to build a smaller model, that's maybe the use case that we have seen until now, that you like build a smaller model and that you somehow compress these things. when you do this type of knowledge distillation, what typically you're doing is that you're focusing on a specific task or domain or something. I mean, when we want to distill knowledge, typically we're not, I mean, one interesting thing of large language models is that you can apply them to many domains. They can do many different tasks if you know it, like you know it from ChatGPT or something. If you're interested in like porting things to a small model, a typical scenario is that you're not interested in being good at everything, but you want to do a specific task be very good. And there you might not need the full power of all the different of the large models, but you try to distill it into a smaller one. So therefore, the first one is to identify this type of target skills or domains. And then we need to have some seed knowledge. That can be either a data set, that's more the typical thing, where you like have data and then you maybe label it. That's how we saw it until now. With language models, the interesting thing is that it can also be instructions. So there's where you describe the task and the model can then generate data based on the descriptions again. Based on that, there is then the knowledge elicitation. The idea is now we have to get the knowledge out of the teacher model. So that is the first big task. So for language models, that's typically that you need to get some, again, input-output pairs, like in all machine learning. In language model, that's typically like you have question and answer pairs, because the input as well as the output is text, as we have seen. So you want to have something like that. And then you need to do some training on your student model based on this generated knowledge that you want to have there. So let's focus on these two last steps, on the extraction of the knowledge and this distillation algorithm. So for this one, in an overview, you can summarize this into like 6 possible ways of doing that. Some is what we have seen already, some there is more because language models can add more things to that. So the labeling is maybe the most standard way you're doing is, so you take your input, then you have maybe some instructions and examples, and you use a strong teacher model to generate your labels. That's what we have seen before. It's just labeling and that what you can do. You can also do what is like the expansion. So where we are not having the input data, you only have instructions. So first you generate your input data, and then you put your labels and maybe update them. So that is maybe more interesting. We'll see that. So that you're not really have to get all the data. You can, in language model, also say, generate me five dialogues or something, and it will generate 5 dialogues, and you can use them. So there's also this type of expansion. You can also do like what is called data curation, so that you have some meta information that you are given, okay, now do a dialogue like a student teacher, now do a dialogue like a business person or something like that. What we have seen until now is you can also try to extract sometimes intermediate features and distribution. Of course, depending on what is your teacher model, that's again then the same way as you had in the knowledge distillation. You can do probability distributions or hidden representations and things like that. And what is maybe interesting is that you not only have to give labels, a lot of them is also used to like give some type of feedback. So you put your input, you generate several outputs by your student, and then the teacher model should give like some type of feedback with how good they are, and you can use that again for training. And a similar one, that feedback is that you're doing some type of filtering. So you're not generating many, but you're selecting someone and there to do then self-distillation. How you do the training is, we have seen it's again very similar. You can do supervised fine-tuning, so normal learning. You can like use the guidance, what we learned today. There's also some type of reinforcement learning or rank optimization there. So in total, you see there's a correlation, but you have a lot more power in language model. You can not only do labeling, you can also give like some feedback or selection and so on. What you see there is already that you can do it in a more natural language way, and not like strictly based on the classes that you have. Yeah, so in total, what we have covered today is we looked into knowledge distillation. We've seen mainly three different ways of doing knowledge distillation. Then we looked at sequence models, why it's maybe more challenging, also data augmentation, and then using that in large language models. Before we close for today, do you have any more questions? Good, then thanks a lot, and then see you again on Thursday.